Hello everyone. In this video, I'm going to discuss a strategy for solving maxima and minima word problems. Before I discuss the steps, I would like to start with an example. So take a moment and read this example. Find the pair of positive number whose sum is 70 and whose product is a maximum. So what we want to do here is we want to maximize the product of two numbers. Since we have to choose two numbers, so let's say x be the first number and y be the second positive number. And the condition is given that the sum of two positive numbers is 70. So from there we get our first equation that x plus y equals to 70. And we want to maximize product. So let P be the product. So if we write the product, so it's going to be x times y. So these are our two equations. So now we notice that product is a function in terms of x and y. So our goal is to convert the main function into one variable only. So it means we need to eliminate one of the variables x or y. We want our product only in terms of one variable, single variable. So in order to eliminate x or y, we can use the first relationship. From here, we can find the value of y and put in our second equation. So from here, y is equal to 70 minus x. So this implies our main function becomes p only as a function of x times y. So in place of y, we write 70 minus x. So our product function is 70x minus x square. So px is 70x minus x square. So this is our main equation or main function. So we want to maximize this. In order to maximize this, first we want to find the critical values of this function. It means we need to set the first derivative equal to 0. The first derivative of px would be, so derivative of 70x is 70 and derivative of negative x squared is negative 2x. So this implies, so if I set that equal to 0, so 70 minus 2x equal to 0, and from here we get 70 equals to 2x. Since our goal is to find what is the critical value, so x is 70 over 2, which is 35. So this is our critical value. So now we're going to test whether this is a value of maxima or minima. For that, we can use the second derivative test. So let's take the derivative of this once again. So second derivative would be negative 2. So which is always negative. So it doesn't matter. So if you put x equal to 35, your critical value here. So again, it's negative 2. So which is negative less than 0. Second derivative negative means less than, so concave down. So that means it's a point of maxima. So our product is maximum when x is 35. What should be the other positive number then? So if x is 35, y is what? So since y is equal to 70 minus x, it means y is 70 minus 35, which is 35. So therefore, the final answer would be the product is maximized when x and y are both 35, when both the numbers are 35. So based on the steps in this example, I would like to summarize the strategy for solving maximum and minimum problems. So the first step is express the quantity to be maximized or minimized as a function of one variable. So let's say you have many variables in the beginning, so we can start with two. So first step is either convert in terms of x only or convert the function in terms of y only. So only one variable. And then we need to use the first or second derivative test to find the relative maxima or minima. But since our goal is to find the absolute maxima minima, so if there are more than one critical value, so we also check at the endpoints of the domain. So what is the value of the function at the endpoints? And based on steps 2 and 3, so you're going to see what is the maximum or what is the absolute minimum value. So what is the maximum value of all of them and what is the minimum value of all of them? So determine the absolute maxima minima from steps 2 and 3. So check at the critical values and also check at the endpoints. So that is our little summary. So now we're going to do some more problems and we're going to follow all these steps in those problems. So take a moment and read our example number 1. So in this one, we are given a reaction rate which is dependent on the amount of reactant at any time. And this is the equation. So what we need to find is for what value of x. So for what value of x, the reaction rate is maximum. So first step is that the function that you want to maximize or minimize, you should write that as a single variable in terms of single variable. So here we are already given the function in terms of single variable. So step 1 is already there. And then we need to find the critical values and the relative maxima or minima. So in this case, we need to use our first derivative or second derivative test. So first derivative of this would be, so before taking the derivative, I would like to expand it because I don't want to use the product rule. So I can just simply use the power rule in this case. So when we expand it, we get, so 6.2 times 25.2 times x minus 6.2 times x square. So I simply just expanded it. So first derivative would be, so scalar as it is, and derivative of x is just 1. I don't want to do this multiplication because I know it's going to get cancelled in the end. So 6.2 times 2x, right? So similarly, if we also need second derivative because we can use the second derivative test. So derivative of a constant is 0 and derivative of this is this. And one thing we notice that this value is always negative regardless of what our critical value comes. So it means it's gonna be concave down. So that means we're gonna get a point of maxima at our critical value. And for critical value, so we've put the first derivative equal to 0. So critical values, so put this equal to 0. So this implies our first derivative equal to 0. And from here, we're going to solve for x. So 2 times 6.2, x equal to 6.2 times 25.2. So dividing both sides by this quantity. So we get, and now you will notice that I was telling you that 6.2 gonna get cancelled in the end. So 25.2 divided by 2 is 12.6. So that is our critical value. So we have only one critical value and we know that this critical value gives us a point of maxima. So the maxima happens at this value. So therefore the reaction rate will be maximum. So reaction rate will be maximum when the amount of reactant is 12.6. So in this case, we had only one critical value. So there was no question of checking the endpoints and stuff. Let's try one more example. So pause this video and take a moment to read this example. So we are given two identical side-by-side rectangular plots and they are to be enclosed by a new fence using an existing fence as one of the sides of the two plots. So this one is existing fence and the new one that we are interested is gonna be our solid lines here. So all this is going to be the new fencing. And our goal is to find the minimum amount of fencing. So minimum amount of fencing required to enclose an area of 1200 square feet. So this area is 1200 square feet together. So we have two plots, and if we are looking for the highlighted fencing, so let's say the length is x, the dimensions of one rectangle are x and y. So it means this length is also x, this length is also x, and this length is y. So whenever we have to solve a maxima or minima problem, first step is define the function. So here our goal is to minimize the perimeter or minimize the amount of fencing. Our function in terms of x and y can be, so 3x, so we have 3x plus 2y. So that is the total length of our fencing. And then we need to convert this function into a single variable. And in order to eliminate one of the variables, we're going to use the other piece of information that we know. So we know that it encloses an area of 1200 square feet. So area is 1200. So which means, so what is the area of this rectangle? So one length is 2y and the dimensions are 2y and x, so area would be 2y times x. From here we get y is equal to 1200 over 2x, so y is equal to 600 over x. And now we can use this information in our original fxy and we can get rid of y. Thus, our function becomes only in terms of x, and we get 3x plus 2y. So in place of y, we write 600 over x. So overall, we get 3x plus 1200 over x. So that is our main function. Or if you want, because I know I have to take the derivative, so I'm just going to write this as x raised to power -1. So our goal is to minimize fx, and for that first we need to find the critical values. And in order to find the critical value, we know that we need to find our first and second derivative so that we can use our tests. So first derivative in this case is going to be 3, and then bring the power down, which is -1, and reduce the power by 1. And also I'm going to find the second derivative. So in this case, the second derivative is going to be -2 times 1200 x raised to power -3. So overall we get 2400 x raised to power -3, or 2400 over x raised to power 3. So in order to find our critical value, we plug in the first derivative equal to 0. So it means 3 minus 1200 over x square equal to 0. And let's just solve this for x. So we get 3 equals to 1200 over x square, or in other words, x square is equal to square root of, sorry, is equal to 1200 over 3. So which gives us 400. So x squared equals to 400, or x equals to plus minus 20. Since we know that the length or the dimensions cannot be negative, so domain is x greater than 0. So there is only one critical value, which is when x is 20 feet. So now we're going to use our second derivative test and see whether this is a point of maxima or minima. So we look at our second derivative, and even if we look at the critical value in the second derivative, and we see that this value is always going to be positive regardless of any value of x, because x is always positive. So second derivative positive means concave upward. Concave upward means we have a point of minima. Thus, minimum amount of fencing happens when axis 20 feet. And since this is our function f, the amount of fencing, so we're going to find f when axis 20. So 3 times 20 plus 1200 over 20, so which is 120 feet. So therefore, minimum amount of fencing required is 120 feet to enclose an area of 1200 square feet. I hope that makes sense. So the gist of this video is that in order to solve any maxima or minima problem, first we find the quantity that we want to maximize or minimize and write that as a function of one variable. If there are more than one variables involved, we are always given some additional information that we can use to eliminate and then write the function in terms of one variable. And then we use the first or second derivative test to find the relative maxima or minima. If there are more than one critical values, we also look at the endpoints of the domain for the possible higher or lower values of function. And based on our information in step 2 and 3, we find the absolute maxima or minima of the problem. I'll do a couple of more examples which are a little bit more complicated in the next video. So if you're interested, please do watch that video as well. Thanks for watching.